Okay, welcome back. So in this part we've finally completed making all of these subcomponents that we need to put together the whole machine, and in this part we're going to actually do it, put it together. So this diagram has almost all of the logic. Remember that we added one thing, which was the signed flag to the decoder, and the signed flag lets us make a distinction between signed and unsigned for set less than, and it also lets us make a distinction between unsigned byte loads and signed byte loads. We're going to add logic to do both of those things. However, before we get started, I do want to talk briefly about the decoder. So I found a couple of bugs while I was testing it, and I figured I might as well point them out. So I've fixed them in this diagram, and I've added some comment wires right by each of them, describing what the problem was or how to fix it. So over here, this NOT gate was on the wrong wire, it was on the R-type wire. This NOT gate was missing, and so were these two buffers. The control type was missing a little bit of logic on this pin, and also these two pins were swapped. And then over here, remember in the last part I mentioned that it's really important that the ALU is doing subtraction for the branch equal and branch not equal instructions. And our decoder wasn't actually doing that, so these buffers are connected to branch equal and branch not equal, so now that will work correctly. Okay, so going back to the architecture. We can get started now. So we're going to start by just dropping a program component in here. Obviously this will be where the program is stored, but it's also the best place to start because it's the leftmost side of the data path. The first thing we need to do once we have an instruction is we need to unpack it into its different fields. And so what we have are all the different fields of the instruction, as you would see in the green sheet. So the top one is the jump address for J-type instructions. Then we have the register addresses. We can give these comments. So this is jump adder. This is RS, RT, RD. This one is called shamped, which is short for shift amount, and I'll come back to that in a second. This one is the immediate. This one is the opcode, and this one is the funct code. So the shift amount is for operations that bit shift by a constant amount, and there are various reasons that MIPS decided to use a different field for that instead of just using the immediate. We're not going to implement the bit shifting operations, so we're just going to not connect this wire to anything. But the bit shifting operations are an easy extension to add to the machine if you want, so this is the wire that you would need. Alright, so you may remember from our decoder video, there it is. The decoder takes exactly two inputs, and those inputs are these bottom two wires here, the opcode and the funct. So we can just connect these straight in, and now we have all the control signals that we need for our machine coming out of the decoder. One other thing that we want to do before we start hooking stuff up is we want to set up the computer to crash if it sees an instruction that it doesn't recognize. So this halt component will make the computer stop if the data coming out of the 64-bit program is ever an invalid instruction. So that's good. Alright, so now we can start working our way through the data path. So the first thing that happens once we have unpacked our instruction is we have to get everything out of the data memory. Or, sorry, not the data memory, the register file. So we'll drop in a register file, and I'm going to make very liberal use of horizontal space in this build. I'm not going to try and make things compact here. And so the A read line is always connected to RS, and the B read line is always connected to RT. There's one other register address on the register file, which is the write address. Which register are we going to write to? And there are four possibilities. So if you look at the... Sorry, there we go. If you look at the diagram that we've been using, you'll see that there's only a two-way multiplexer on that diagram, but I just grabbed a 4-way multiplexer. So the reason that I did that is because we are implementing another couple of instructions that that machine does not implement, which are the jump and link instructions. And I'm not sure why that machine doesn't implement them, because they're actually very important. They're how you do function calls. But they have a side effect of adding another way that you can cause a write to the register file, and I will talk a little bit more later about exactly what's going on when we wire it up. But the important thing to note is that it can force the target register to be register 31. So there we go. And this controls the write address over there. And we'll worry about the enable and data pins later. So the other thing is what's coming in on these wires. Well, this pin, this one, is going to be a control line that tells us whether or not the current instruction is a link instruction. So we'll wire that up all the way later, but that's what it will tell us. And notice that it's connected to the more significant bit of the select signal. So when this line comes on, we're going to be selecting between these two inputs, the bottom two, but when it's off, we're going to be selecting between the top two inputs. And the top two inputs are the ones that are in the diagram. So the diagram there tells us that we need to use RD source to pick between using RD and RT. And then I also know from how the link works that we're going to want to use RD in this case. So we want to use RD by default, but when RD source comes on, we want to use RT instead, like this. So that's the write address. And so these are all the input signals to the register file that we have right now. I mean, we have a write enable pin on here, but we'll connect it later. For now, we're going to go straight through the data path. So now we have our A line and our B line coming out of the register file over here. And the next thing to do is arithmetic. So if we take our MIPS ALU, and we just plop it down over here, the A line goes straight through. But if we look at the diagram, the B line is not so simple, right? The argument here can come from several different places. So we need to make sure that we pick the right one. So we're going to use a multiplexer, because we're selecting between various signals. So this is what multiplexers are for. And I think we talked briefly in the decoder video about when we use each one. But the important thing is that when all the control signals are off, when all the control signals are off, we're going to take from the B output of the register file. But when the more significant bit comes on, which is this one for this multiplexer component, those are swapped, which was a mistake on my part. When the more significant bit comes on, we want to look at these instead. And so remember that what we did for these pins here is that one of them tells us whether we should use an immediate at all, and that one is the less significant bit, this one. The other one tells us if the immediate should be signed or unsigned, which is this one. And it's never the case that we care about this pin, right? Because this pin would be, we're not using an immediate, but we should care about whether or not that immediate is signed. And we're not using an immediate, so that doesn't make any sense. So this pin's going to just stay unconnected. But these two pins need to be connected to a signed and unsigned version of the immediate. And so this is where those sign extenders come in. So the immediate is a byte value, or sorry, it's a double byte value. And so in order to sign extend that, we need a sign extender for double byte values, which are also called halves. And all we need to do is wire that sign extender up to the immediate from over here. Sorry, there was an issue on my other monitor. Okay, there we go. And then, of course, we also need the unsigned version to come through as well. So now we get two wires. And these are on the wrong side, so we're going to have to cross the wires, but this one goes all the way up here, and this one goes there. Alright. So now, how do we control these things? Well, the control type for the ALU-B input comes from the pin over here labeled ALU source, or possibly ALU source 2, which is this pin, I believe. Double check that. Yeah, this one. And so we have 2 bits of control over here, and they're separated. We have a byte wire over here, and the byte wire is just carrying both pieces of information on it, but we need to break them out. And so we could put a byte splitter over here, like this, and grab the bottom bits. The byte splitter is very big, and we only care about 2 of them. So instead I have this custom component called split3, and all it is inside is just a byte splitter, but it only splits out the top 3 bits, and in this case we don't even care about all 3, we only care about 2 of them, and we wire them up like this. And so this gives us the ALU-B input, which we can now connect. The only other control signal for the ALU is the operation that it should perform. And that one is just coming out of the decoder on this line. So we can just hook that right up. Oh, I was right the first time. Oops. All right, there we go. Okay, and so now we have our ALU math result and a bunch of flags, which we can label. Do it like this, I guess. So this one is the negative flag, or the sign flag. This one is the overflow flag. This one is the 0 flag. And this one is the carry. And we will need these in order to do the set less than thing. So you can see in the diagram, which, by the way, I recommend you keep open on the side somewhere, because I'm not going to keep tabbing out to it. We can see on the diagram that normally for set less than, we just need to choose between the result of the ALU and the value of the carry flag. But it turns out that that's actually not good enough for our purposes, because we also want to support unsigned less than, right? We want to support both. So actually what we want to do... Oh, only using the negative flag is actually wrong. There are some cases where that will give you the wrong result. So actually what we want to do is we want to take the exclusive OR of the overflow and the negative. And that one tells us if we have signed less than. What the carry tells us is that we have unsigned less than, and we'll wire up the control signals to pick between the correct ones. And then in either of the cases where we're not doing a set less than operation, we don't care whether the operation was signed or not, we want to return the ALU results. So we want to connect the ALU result to both of these pins. The 0 isn't used for determining these things. The 0 is useful because when you do subtraction, as I mentioned earlier, the 0 line only comes on if the values were equal, and we're going to want to connect that to our program counter controller over here, which we will wire up later. Okay, so control signals for this one are just the signed flag, which is going to be on this wire, and it's going to also have to go way out there, so I'm just going to preempt it. And the other control signal is this one, I believe, which is labeled set less than. So this control signal tells us if the operation that we're doing is a set less than operation in the first place. That's not enough space. Okay, this will work. And so when the operation is a set less than operation, we want to switch from using the ALU result to using one of these comparison results. So we want to flip the more significant bit, which is this one. And the other one is the signed bit, which tells us which one of those two outputs we should use. And so now we have our ALU result. But this isn't always the result of the instruction, right? Some of the instructions have memory accesses as part of what they do. And so for those instructions, we need to talk about the addressing mode, which is base plus offset. So if you look at the load word instruction on the green sheet, as we talked about in part 1, you can see that it's actually an I-type instruction. It takes an immediate. And so what's going on is that the source register is the address that you want to use, but maybe not the whole address. It's what's called the base address. And then to get the actual address, you add the immediate to it. So when we do a load word or a store word or a store byte instruction, we have the ALU set to do an add operation. And it will perform that add operation on this value coming out of the A register, and on the sign extended immediate, which is this value. And the result is going to be an address, so I'll switch to my address color. And might as well do it like this. And then we have the last section of the data path, which is data memory. And, I don't know, I'll leave some space, but not too much. You might notice I've added a load pin to the data memory. We're going to connect that, but it doesn't do anything inside the data memory component. This is just in a disconnected pin. My hope is that soon TC will allow me to mark that pin as, hey, if this pin is off, and these pins are also off, don't simulate this component at all, because simulating this component is really slow, and I will show later that the machine that we're building simulates pretty slow overall because of basically entirely this component, which is unfortunate. But that's what we have. So anyway, like I said, this one is the address. And remember, when the data memory outputs a result, it outputs all 4 bytes starting at the selected address, regardless of the bottom 2 bits of the address line. So we're always going to get 4 bytes out here, and they don't care about the bottom 2 bits. But if we're trying to load a byte, we actually do care about the bottom 2 bits, because they tell us which one of these bytes we actually care about. And so, in order to get a result for... let's see, I think there should be good. In order to get a result for the byte load operations, we need to split off the bottom 2 bits and use them to control this multiplexer. So, the bottom 2 bits of the address we can break off with this thing again. And remember, what's going on here is when we plug this 64-bit wire into an 8-bit input, it just takes the bottom byte, and then the split 3 is just picking off the top 2 bytes. In fact, the top 3 bytes, but we only care about 2 of them. I didn't need to switch colors there. So we can take this and connect it to the more significant byte, and this one, and connect it to the less significant byte. And so this gives us the result for byte load operations. But what about word load operations? Now we want all 4 of these bytes. So for the word load operations, we have to take a 64-bit maker like this. Oops. I want to leave a little bit of space there. And we have to connect the bytes like this, so that now the result over here is the word that we wanted to read. And in this case, it's the byte that we wanted to read. Now remember, I mentioned earlier, we're also going to be supporting signed byte reads. So that's why we have this byte sign extender. So sometimes we'll need a signed result, and sometimes we'll need an unsigned result. And to select between those, like you should always do when selecting between signals, we want a multiplexer. And then we further have to select between the load word result and the load byte result, and so that's another multiplexer right here. And both of those are control signals. So this is the signed wire that we pulled over earlier. That controls whether we're doing a signed or unsigned byte read. And this one controls whether we're doing a word or a byte read. And that control signal is coming out of the decoder over here. So this one, when this signal comes on, we're supposed to read a byte, and when it's off, we're supposed to read a word. Okay. And so now we officially have all of the major parts of the backwards flowing data path. So we've computed a result, and now we need to get it back to the register file. So we're going to need to pick between memory results and ALU results. And in order to do that, we can use this wire over here. This pin is labeled memory load, and this one tells us if we should load from memory. So in fact, we can also go over here and connect that to the load pin of the data memory, which, like I said, doesn't do anything now, but hopefully will do something in the future. We can also connect it to this multiplexer. And then the data memory has two other controls. Those are the byte write enable and the word write enable. There we go. All right, yeah, that looks right. Okay. And so these are two more signals that are just coming straight off the decoder. So you can bring these over here and connect them like that. And so now we have all the control signals to the data memory. The last thing is the value being stored over here. And if you look at the green sheet, you'll see that the value being stored is always the value coming off of the B read line of the register file. And so we can just connect that straight across. No fuss, no need to modify anything. So before we move on, I just want to talk about one last thing. We have this pin on our data memory. If you'll recall, this pin tells us if our data memory can handle the requested address. And the reason that that's a problem is because MIPS sort of requires that the data memory be 4 gigabytes, but Turing Complete can't handle that, and even if it could, it would probably simulate slow, so we don't really want to handle it. Instead, our data memory just sets aside a few hundred kilobytes in relevant, what are called segments of memory. So we have a segment for the stack and a couple of segments for data memory. When this pin comes on, it means that the address isn't in any one of the known segments. And so if we're trying to do a memory access while this pin is on, we should raise what's called a segmentation fault, or seg fault for short, and that should crash the computer. So what we want to do is we want to check, are we doing any kind of memory access? Doesn't matter which one, load, store, store word, or store byte, they should all cause a problem. And if we are, and the, how do I want to wire this? If we are, and that accept pin is on, we want to crash the computer, and so we can do that with another halt component, and the message over here can just be segfault. Okay. And so when our program is done executing, we'll actually intentionally cause a segfault to get the simulation to stop, and I'll show an example of that later. Okay, so we're sort of in the home stretch here. This value is almost the whole result for the ALU, but not quite. The reason that it's not quite the whole result is that there is one other, let's say, type of instruction that can write data into the register file, and it's called an LUI instruction. LUI is short for load upper immediate, and this pin is also labeled LUI. And what LUI does, basically, is it takes the 16-bit immediate value and it loads it into the top 16 bits of the destination register instead of into the bottom 16 bits. The reason that that's useful is because sometimes you want to load a 32-bit immediate value into a register. Like, for example, say you want to set a register to -1. There are smarter ways to do it, but you could do it by trying to load a 32-bit immediate. What you would do is you would first load upper immediate, all ones, into the top 16 bits, and then you would OR-I that with, I guess, all ones to get -1 into the bottom 16 bits. Or if you wanted -2, you would OR it with 15 ones and then a 0, etc., that kind of thing. So if we have an LUI operation, we actually don't want to use this value. We want to use the immediate value from down here. Let's see. At my diagram. I think I want to put this over here. That doesn't look right. I think I want to put it over here. We want to use this immediate value, but we don't want to use it directly. We want to use it shifted left by 16 places. And so in order to control that, we can take our shift left component and a byte constant, set the byte constant to 16, like so. And now we have the upper immediate. And all we need to do is now pick the correct value between the upper immediate and the computation result. And like always, we're going to do that with a multiplexer. And then connect that multiplexer to our control signal, like so. Okay. Great. So with that, we now have the computation result over here, and we can just send that straight into the write data over there. And then finally, there's the write enable pin, which is this output on the decoder. Okay, so with that, we can already do simple R-type instructions, and in order to support I-type instructions, all we need to do is connect this input to its decoder signal. And remember, that is the RD source control signal over there. So now we could execute a single simple instruction, and I unfortunately don't have an opcode for one on hand. Or actually, wait, I guess... Oh, no, interesting. Program component was showing that there was a program in there. I don't know why. But anyway, if you wanted to hand assemble an operation, like say, add the 0 register to the immediate 15 and store the result in register 2, your machine should be able to execute that instruction now, and you would see this, this watch state, the third one on the top row, should switch to 15, for example. And we'll run an example program later. I won't talk about it too much in depth, but I will show the listing, which you can copy over. Yeah, so the only thing that we have left to do in order to make a full machine is to implement the program counter and the control flow logic. So in the last video, we talked about the program counter control unit over here. And in this video, all we have to do is wire it up. So we can see over here, this leftmost pin, this one, wants the jump address. And so we can just bring the jump address over from the instruction unpack. The next pin over wants the A output of the register file, like so. And the next pin over wants something called the branch offset. Now the branch offset is the sign extended immediate. It tells us how many instructions to jump forward or back when we take the branch. So positive numbers jump forward, negative numbers jump back. However, since instructions are 4 bytes, their addresses are always divisible by 4, which means the bottom 2 bits are 0. And there's no reason to waste 2 bits of the immediate always storing zeros. So instead, we drop the zeros, and now we need to add them back. So in order to get the proper branch offset, we have to take the sign extended immediate from over here, and in fact we can use an address color, and we have to shift it left 2 bits. Do it like that. Okay, and now that's the branch offset. Then we need the control, which tells the unit which type of control flow should it use. Should it fall through to the next instruction in sequence? Should it jump? Should it jump to the value in this register, or should it branch? And if it should branch, it needs to know, well, were the A and B values equal? Because that's the condition that controls branching. And so for that, we need the 0 flag output from the ALU. Okay. So the last type of input that we need is the program counter. Like that, I guess. And then we'll get 3 outputs. So the first output, which I'm gonna wire over like this, I think. The first output is the next value that the program counter should have. Second output over here is the address of the next instruction in sequence, which won't always be the next value of the program counter, but if we're doing a jump and link instruction, we still want it, because if we're doing a jump and link instruction, then we're supposed to write this value into the address addressed by the right address pin. And so this is actually another way that the value going into the right data can be switched. And so we need another multiplexer to control which one we should do. So we can toss another multiplexer over here. Move this down there. Actually, that was wrong. There we go. Yeah. Because when the link pin comes on, that's when we want to switch to using the link address. And then this last output is the link control. So this output tells us if we're doing a jump and link or a jump and link register instruction, and that just controls these 2 multiplexers like I mentioned earlier. So now all we have to do is hook up a register to hold the program counter. And we're using a register and not a counter because the PC control is already handling that increment. There's no need to do it twice. So we can just wire that over. And then we always want to read, and we always want to write, like that. Okay. So we're almost there. There's a couple more gotchas, which I will explain in a second, but we basically have all the details. So now we can just take this instruction address, send it over to the 64-bit program, and there's now just one catch. The program counter over here is always storing a value that's divisible by 4. Again, so the bottom 2 bits are always 0. The 64-bit program component doesn't like that, right? Because this one is 64-bit word addressable. So if we want to switch to the second instruction, we want to go from address 0 to address 1, not address 0 to address 4. So this time we want to go the other way. We want to shift right instead of shifting left. But it's exactly the same. We want to shift by 2 places. Okay. And so now we have a working computer. We could put a program in here. We can run it. There's one other thing that I want to talk about quickly, which is that it is actually possible by branching backwards mainly for this 64-bit wire to have an actual 64-bit value on it instead of a 32-bit value. The 64-bit program ignores everything except the bottom 16 bits of the address. So that's not a problem per se. The computer will still work. but it will mess with the display in the assembly editor. So if you try and send a 64-bit address to the program component, it'll still return the instruction that's addressed by the bottom 16 bits, but the assembly editor won't show you which line of code it's on. And that's a little bit annoying. So we can fix that easily by just taking a 64-bit AND component, not a byte AND component, like this, and connecting the 64-bit constant, which is just all of the bottom 32 bits. And so that way, if the value that comes in is any bigger than this, it'll just mask off the top 32 bits and we'll be left with the bits that we actually care about. Okay, and so this is the whole machine. I should have in my clipboard a program for this machine, so drop that in there. Yep. There we go. And so this is a little program that I assembled by hand, because the Turing Complete assembler is currently not powerful enough to support MIPS assembly syntax. I thought it was quite enjoyable to assemble this by hand. At the very least, I think it's a good mental exercise, so I would recommend trying to assemble a program of your own at some point, but, you know. So anyway, this is a simple Fibonacci program, and it uses the slow recursive algorithms. This is a good stress test, and it demonstrates how you do function calls and how you use a stack in MIPS assembly. I don't want to talk about this program too much, but as you copy the listing over, you should try and get a sense of what it's doing, and of course, as always, you can feel free to ask questions. The main thing to note is that the Fibonacci number that it will compute is this 16-bit immediate right here. So there's a 7 there right now, so it's going to compute the 7th Fibonacci number, which is 13. If you change that to 8, it will compute the 8th Fibonacci number, which is 21, etc. But like I said, this is using the slow recursive algorithm, so if you put a big number there, it's going to take a very, very long time for the computer to finish, so I recommend not doing that. I think 7 is a good number. And then once this call to the Fibonacci function returns, we attempt to load a word from address 0, and that will cause a seg fault, like I mentioned earlier, which will make the computer halt. So here you can see the first half of the program. Can pause the video and copy that over. And then down here is the second half of the program. And in this half, we use the data memory as a stack and make the recursive calls and do math. So you can pause the video and copy that over too. And if I run this program, first I want to make sure we can see the data memory. If I run this program, you can watch the values in the data memory as they start changing or not. What did I do wrong? I see the address to this is not changing. Let's see, it's getting a 4 in. And a 4 over there. And this is the correct constant. I am very confused. What is happening? Okay, let's run a test quickly. Uh-huh. I think this register is just broken. Try a different register. And if that doesn't work, I have a different build of this machine that I can pull up. And I know that that was working in this Turing Complete session because I was looking at it before I started recording. Yeah, there we go. Okay, that was very strange. Okay, anyway. So I can run this program now, and we can watch the values in the data memory change And so you can see this first one on the second row is the register that we're passing the argument in. And these last two registers on the top row are being used for scratch arithmetic, and then also the third one is where the Fibonacci function returns its value. So as it's working, you can see it's getting bigger and bigger Fibonacci numbers, and there, in the second to last register in the top row, you can see the result, 13, and then you can also see that the computer halted with a seg fault. So this is a good sign. This is a very strong indication that we've built the whole computer correctly, because that function really stress tests most of the operations that we have. It doesn't test the set less than operations, and it doesn't test the signed or unsigned even byte loads. So if you want to test those things, I recommend you write your own program that uses them, and then try and assemble it by hand, and feel free to ask for help with that. But yeah, this is the whole machine. So this is the end of book 1, so to speak, of the MIPS series. We've put together a whole MIPS machine that can run a subset of real MIPS programs. I suggest trying to add some operations to this as you see fit. So some easy ones to add are the shift instructions, but there are more than that as well. In the next book, so to speak, of this series, we will talk about how to pipeline this machine and what that means and why you would even want to do it. And, sorry, excuse me. And I'm really excited for that part. Personally, that was actually why I started this series, so that I could talk about pipelining, because that's something that I know how to teach that TC didn't already get into. And so I'm going to keep working on these videos, and soon we'll be talking about pipelining. And then also, as soon as Turing Complete supports custom level packs, which I'm very hopeful are coming soon, I will be making a set of custom level packs that goes along with this series. So custom level pack set where we build the MIPS machine that we just built from the start. And then also an add-on level pack that talks about pipelining, and then probably another pack that talks about how real multipliers work. So the product of nibbles level makes you build a single cycle multiplier. I'm going to talk about how you would build a multiplier that's more like what you would see in a real hardware, which can also do division, so that's convenient. And then I may also make a level pack about floating point units, and all of that will be connected to this machine. So that's an idea of where I'm hoping to go with this. Hopefully that's exciting to you, it's exciting to me. And yeah, thanks for watching this far, and I hope you've enjoyed.